There are few things more humbling than contemplating the scale of the cosmos. From the surface of Earth, our night skies offer a glimpse into the vastness beyond. We see stars twinkling in constellations, faint smudges that mark distant galaxies, and the faint band of lights stretching across the sky that we call the Milky Way. But the true scope of the universe cannot be grasped with the naked eye. It must be imagined. In our own galaxy, the Milky Way, astronomers estimate that there are around 100 billion stars. But that number is not fixed. With better instruments and deeper surveys, it might be 200 billion or 400 billion. No one truly knows. Each star may host a planetary system. Each system may hold worlds of its own. And our galaxy is just one among perhaps 100 billion others scattered across the observable universe, or 200 billion, or more. Every step forward in technology has brought new surprises, revealing a universe more complex and more populated than we had dared assume. 100 years ago, the known universe consisted of a single galaxy, our own. In 1923, Edwin Hubble identified a Cepheid variable star in what we now call the Andromeda Galaxy, proving it was far beyond the bounds of the Milky Way. This single discovery expanded the known universe by a factor of millions. Since then, each generation has added layers of depth to our cosmic understanding. We now know that galaxies are not isolated. They cluster. They form filaments and walls woven into an immense cosmic web that stretches hundreds of millions of light years across. And yet, all of this, all of the stars and galaxies we can detect, make up less than 5% of what exists. The rest we cannot see. We call it dark matter and dark energy, names that signal not understanding but absence. It is in this absence that much of the mystery resides. And this is why, even with our growing knowledge, we are still in the early days of cosmic discovery. But discovery faces limits. The universe is vast, not only in space, but in time. The light from the most distant galaxies has taken billions of years to reach us. What we see is not what is, but what was. And space itself expands. The farther away an object is, the faster it appears to recede from us. Some galaxies are moving away faster than light, not because they break the rules of physics, but because the fabric of space between us stretches so swiftly. This expansion places a hard boundary on our reach. There are regions of the universe whose light will never reach us. Not now, not ever. They are beyond the cosmic event horizon, the limit of the observable universe. What lies beyond remains unknowable. We can imagine, but never observe. Even within our observable domain, the scale of cosmic distances makes exploration a daunting challenge. Consider Voyager 1. Launched in 1977, it is the most distant human-made object. After more than 4 decades, it has left the heliosphere, the bubble of particles and magnetic fields generated by the sun. It is now traveling through interstellar space, and yet it has only crossed a tiny fraction of the distance to the nearest star. At its current speed, it would take more than 70,000 years to reach Proxima Centauri, our closest stellar neighbor. Voyager 1 is a triumph, but also a reminder. The stars are far. What Voyager symbolizes is not just distance, but time. Its mission has outlived its creators. It carries a golden record, inscribed with sounds and images from Earth, intended for any intelligence that might one day encounter it. But that day, if it ever comes, is likely to be unimaginably far in the future. The Voyager spacecraft will drift, silent and cold, for eons, long after Earth itself may have changed beyond recognition. So how do we explore the universe if we cannot go to it? We use light. Every object in the cosmos emits or reflects light across a wide range of wavelengths. Some of that light reaches us, and with telescopes, we can capture it, analyze it, and begin to understand the story it tells. Telescopes are our windows into the universe. The earliest were simple tubes of glass, but they revealed the moons of Jupiter, the rings of Saturn, and the phases of Venus. They confirmed that Earth was not the center. Over time, telescopes grew larger, sharper, and more precise. We moved from lenses to mirrors, from visible light to radio waves, X-rays, gamma rays. Each new wavelength opened a new layer of the universe. Yet even telescopes face limits. On Earth, the atmosphere blurs our view. The larger a telescope mirror becomes, the more it deforms under its own weight. At around 8 meters in diameter, traditional designs begin to fail. Atmospheric turbulence scatters incoming light, washing out fine detail. One solution is to rise above it. The Hubble Space Telescope, launched in 1990, orbits high above Earth. It has revealed some of the most detailed images of the cosmos ever taken. Pillars of gas where stars are born, distant galaxies colliding, light from stars so ancient they formed shortly after the Big Bang. But Hubble is small by ground-based standards, constrained by the size of the rocket that carried it. On Earth, engineers developed new techniques. The Keck telescopes in Hawaii, with 10-meter segmented mirrors, use active optics to adjust their shape in real time. Adaptive optics compensate for atmospheric distortion by tracking guide stars. The result is imagery that rivals that of space-based observatories. Still, we cannot look everywhere. Dust clouds obscure some regions. Some wavelengths are absorbed by Earth's atmosphere, and there is a limit to how faint a signal we can detect. Every photon must journey across the void, survive interference, and reach our instruments intact. In this context, every observation is precious. The light from a distant galaxy may have traveled 13 billion years. A single faint smudge on a detector represents an epoch when the universe was young, dense, and just beginning to form stars. These ancient photons are messengers. They carry with them the fingerprints of their origin, red-shifted, stretched, and softened by the vastness of space. Yet they endure. We gather them patiently. Over days, weeks, months, some telescopes stare at the same patch of sky for hundreds of hours. Slowly, the image deepens. New features emerge. Galaxies multiply. The darkness recedes. Through this process, we build a map, not of geography, but of history, a record of what was. The night sky becomes a time machine. Each star, each nebula, each galaxy is a page in a cosmic archive. We read not just with our eyes, but with our instruments. With spectroscopy, we learn what stars are made of. With parallax, we measure their distance. With motion, we infer their past. And through it all, we remain grounded. We are bound to one planet, circling one star, in one galaxy among billions. Our reach may be limited, but our vision is not. With light, we explore. And with understanding, we begin to belong. As we open this cosmic window, the view is humbling. It's also magnificent. The scale of the universe does not diminish us. It expands us. We are part of it, observers shaped by stardust, studying the stars. In their light, we find questions, and sometimes glimpses of answers. For centuries, humanity has looked skyward and asked what lies beyond. At first, we looked with the naked eye. We mapped the stars into patterns, named constellations, and watched the motions of planets across the sky. But with the invention of the telescope in the early 17th century, our understanding of the cosmos began to transform. The first telescopes were simple refracting tubes. glass lenses that bend light to form an image. Galileo Galilei pointed one at the moon and saw mountains and craters. He turned it toward Jupiter and discovered 4 of its moons. These early instruments were small, but they shattered centuries of assumptions. The heavens were not immutable. They were places of change, complexity, and motion. As the science of optics improved, telescope designs became more ambitious. Reflecting telescopes, which use mirrors instead of lenses, began to dominate. Mirrors avoided the problem of chromatic aberration, the color fringes that refracting lenses could produce, and allowed for larger apertures. Larger apertures meant more light could be gathered, allowing astronomers to see fainter and more distant objects. Throughout the 18th and 19th centuries, ever larger reflecting telescopes were built. They were housed in observatories atop hills or mountains, away from city lights and atmospheric haze. Each generation of telescope brought new discoveries, from the rings of Uranus to the spiral structure of galaxies. The race to build bigger mirrors was driven by a simple truth: more light means more knowledge. But building larger mirrors introduced new problems. A mirror must be precisely shaped to a curve accurate within fractions of a wavelength of light. Any deviation distorts the image. As mirrors grow in size, they become heavier, and that weight creates deformation. A massive mirror mounted at one end and tilted to aim at various parts of the sky begins to sag under its own gravity. The delicate curve bends. The image blurs. By the late 20th century, the practical limit for single-piece telescope mirrors had been reached. Beyond 8 meters in diameter, the challenges of maintaining structural integrity became too great. Even before that, the blurring effects of Earth's atmosphere limited what could be resolved. Twinkling stars are romantic to the naked eye, but to a telescope, they are a problem. Atmospheric turbulence distorts incoming light, smearing fine detail. To overcome these limitations, astronomers pursued 2 paths, one that led upward and one that delved inward. The first path led to space. If Earth's atmosphere is the problem, then why not escape it altogether? This was the thinking behind the Hubble Space Telescope. Launched in 1990 aboard the Space Shuttle Discovery, Hubble orbits Earth at an altitude of about 550 kilometers. Above the atmosphere, it has an unobstructed view of the cosmos. No twinkling, no blurring, just clarity. Hubble carries a 2.4-meter mirror, small by ground-based standards, but capable of extraordinary precision in orbit. Its instruments have captured iconic images: the pillars of creation, deep field views showing thousands of galaxies, and the changing atmospheres of planets in our solar system. Hubble's contribution to astronomy is not just visual. Its spectrographs have measured the expansion rate of the universe, confirmed the presence of exoplanet atmospheres, and helped determine the age of the cosmos. Yet, Hubble came with constraints. Its mirror size was limited by the dimensions of the space shuttle, and servicing it required astronauts, spacewalks, and years of planning. Still, its success proved the value of space-based observation. It also highlighted the cost. Meanwhile, engineers on Earth were developing the second path: new ground-based telescopes that could defeat the very problems that plagued their predecessors. One breakthrough was the concept of segmented mirrors. Rather than forging a single enormous piece of glass, mirrors could be constructed from multiple smaller segments. Each segment would be carefully shaped and mounted on actuators, mechanical devices that could subtly adjust their position in real time. These systems are called active optics. The twin Keck telescopes on Mauna Kea in Hawaii were among the first to implement this technique. Each telescope has a 10-meter mirror composed of 36 hexagonal segments. Sensors monitor the shape of the mirror, and tiny motors behind each segment make constant adjustments to keep the overall surface perfectly curved. Even as the telescope shifts to track objects across the sky, the mirror maintains its precision. But active optics solved only part of the problem. Even with a perfectly shaped mirror, Earth's atmosphere still distorts incoming light. To overcome this, astronomers turned to adaptive optics. This system uses a bright guide star, either a natural star or one created by shining a laser into the upper atmosphere, to measure the distortion in real time. A deformable mirror then changes shape many times per second to cancel out the turbulence. The result is a dramatically sharper image. With adaptive optics, ground-based telescopes can now rival and sometimes surpass the resolution of space-based instruments. Observatories that once blurred the edges of Jupiter's cloud bands can now resolve individual storms. Details on the surfaces of distant moons, once invisible, now emerge with clarity. The universe sharpens into focus. These technologies have enabled a new era of astronomical exploration. Telescopes like the Very Large Telescope in Chile, with its 4 8.2-meter mirrors, use interferometry to combine their light, effectively acting as a single enormous instrument. Radio observatories like ALMA operate at millimeter and sub-millimeter wavelengths, peering through cosmic dust that blocks visible light. Together, these tools allow us to explore the universe across the full electromagnetic spectrum, from gamma rays to radio waves, from hot stars to cold gas clouds, from distant galaxies to nearby planets. Each type of light reveals something different, and each telescope, in its own way, extends the reach of human vision. As telescopes evolved, so too did our understanding of time. Because light travels at a finite speed, every observation is a glimpse into the past. When we look at the moon, we see it as it was 1 second ago, the sun 8 minutes ago, the Andromeda galaxy 2.5 million years ago. With deep space telescopes, we can see light that has traveled for billions of years, light that began its journey when the universe was young. This connection between light, glass, and time is profound. Through lenses and mirrors, through atmosphere and vacuum, we capture not just images, but epochs. We see the universe as it was, and in doing so, we begin to understand what it is. Each photon that strikes a detector is a thread in a tapestry woven across space and time. And so, the telescope, that simple tube of glass, has become a time machine, a bridge between Earth and the stars, a vessel of curiosity and precision. With each improvement, we sharpen our vision. With each observation, we deepen our story. Light guides us, glass shapes it, time reveals its meaning. The cosmos speaks not only in light but also in whispers. Silent waves that pass through space, invisible to the eye yet rich with meaning. Long before modern observatories, humanity knew only the visible spectrum. What we saw was all we could know. But light, as we later discovered, comes in many forms. Beyond red lies infrared, beyond blue, ultraviolet, and further still, an ocean of radiation, radio, microwaves, millimeter waves, each a different voice in the chorus of the universe. To listen to these voices, astronomers needed new instruments. Radio telescopes became the first ears turned toward the cosmos. Unlike optical telescopes that rely on mirrors and lenses, radio telescopes use large metal dishes to collect long wavelength radio signals from space. These signals are faint, often drowned by noise from Earth's atmosphere or human technology. But when filtered and focused, they reveal phenomena that light cannot. Pulsars spinning with atomic precision, jets launched from the hearts of galaxies, and the clouds of hydrogen marking the skeleton of the cosmic web. In 1931, Carl Jansky, a young engineer working for Bell Labs, built a rotating antenna to study static on telephone lines. Instead, he discovered a steady hiss coming from the center of the Milky Way. It was the first detection of radio waves from space. In that moment, a new window on the universe opened. This accidental discovery transformed radio technology into a tool for cosmic inquiry. Radio astronomy soon blossomed. Observatories were built with dishes the size of buildings. The 100-meter Effelsberg radio telescope in Germany, the 305-meter Arecibo Observatory in Puerto Rico, which stood as a giant until its recent collapse, and more recently, the 500-meter Aperture Spherical Telescope in China, or FAST, now the world's largest single-dish radio telescope. These giants scan the sky for fast radio bursts, map hydrogen gas across billions of light years, and search for narrow band signals that might suggest the presence of intelligence elsewhere in the universe. But size alone is not enough. The longer the wavelength, the harder it is to achieve high resolution. A radio dish 100 meters wide still sees a blurry patch of sky. To sharpen the image, astronomers turn to interferometry. Interferometry is a technique where signals from multiple telescopes are combined to act as if they were one enormous dish. It's not about adding their sizes, but about using the distance between them, the baseline, to simulate a larger aperture. The farther apart the telescopes, the finer the detail they can resolve. In principle, two dishes separated by thousands of kilometers can produce an image with the clarity of a telescope as wide as the Earth itself. In the high desert of northern Chile, the Atacama Desert offers ideal conditions for such precision. Dry, elevated, and far from sources of radio interference, it hosts one of the world's most advanced observatories, ALMA, the Atacama Large Millimeter Submillimeter Array. ALMA does not look like a single telescope. It is a constellation of 66 dishes, each 12 or 7 meters wide, spread across the plateau. Working in harmony, they observe the universe in millimeter and submillimeter wavelengths, a realm between radio and infrared. These wavelengths can pierce through dense clouds of cosmic dust that block visible light, revealing the coldest, most hidden regions of space, where stars and planets are born. By using interferometry, ALMA simulates a telescope up to 16 kilometers in diameter. The signals from each dish are recorded with precise timing using atomic clocks to synchronize the data. Then, using powerful computers, the signals are combined to form a single high-resolution image. The result is astonishing clarity: spiral arms of distant galaxies traced by carbon monoxide, dusty rings where planets are coalescing, jets from newborn stars bursting through the interstellar medium. But Chile is not alone. Around the world, radio telescopes join forces to push the limits of resolution. One of the most extraordinary achievements came in 2019, when astronomers released the first image of a black hole's shadow. It was not captured by one telescope, but by many. The Event Horizon Telescope, or EHT, is a global network of radio observatories, from Hawaii to Spain, from the South Pole to the Andes. Together, they form an Earth-sized interferometer. By linking observatories across continents, EHT achieved the resolution needed to image the black hole at the center of galaxy M87, 55 million light-years away. The image showed a ring of emissions surrounding a shadow. the silhouette of the event horizon itself, where space and time collapse. This feat required extraordinary precision. Every observatory recorded petabytes of data, synchronized to fractions of a nanosecond. Because the data volumes were too large to transmit, they were physically shipped to processing centers. Months of computation transformed raw interference patterns into an image, and from that clarity emerged a ring of light, the last photons before falling into darkness, circling a shadow where matter vanishes. Such a result would have been unthinkable just decades ago. But it shows what is possible when instruments are connected, when observations are global, and when human cooperation spans the Earth in service of the stars. EHT proved that with enough coordination, we could peer into the deepest gravitational wells of the cosmos. This idea of linking telescopes to create something larger than the sum of its parts is changing astronomy. In radio, it has become standard. But the principle is expanding. Optical interferometry is being developed. Space-based interferometers are being imagined. One day, we may build a telescope spread across the moon or coordinated swarms in orbit, free from Earth's atmosphere. The goal is always the same: to see what was once invisible, to trace the contours of the cosmos with sharper eyes, to hear the quiet voices carried on long wavelengths. Every new frequency opens new mysteries. Every deeper connection reveals a more intricate design. And every shared effort reminds us that even our smallest discoveries are part of something vast. The sky is not silent. It sings in 1,000 voices. And now we are learning to listen. In the deepest wells of gravity, where space itself bends beyond return, there dwell the most enigmatic objects in the universe: black holes. For centuries, they were only shadows in the equations, whispered possibilities born from mathematics rather than observation. But today, we not only believe in their existence, we have seen them. The idea began not with Einstein, but with Newton. In the 18th century, some thinkers speculated about dark stars, bodies so massive that their escape velocity exceeded the speed of light. It was a curious thought, soon forgotten. Only with the dawn of relativity did the idea return, reformed and sharpened. Einstein's general theory of relativity, published in 1915, reshaped our understanding of gravity. No longer a force acting at a distance, gravity became the curvature of space-time itself, bent by mass and energy. This elegant framework predicted phenomena that Newton's equations never could: gravitational waves, time dilation, and black holes. The mathematics of relativity hinted at regions where the curvature becomes infinite, where mass collapses to a point and space-time folds in on itself. In 1916, Carl Schwarzschild found a solution to Einstein's equations that described such a region. It had a boundary, later called the event horizon. Inside, nothing, not even light, could escape. Still, for decades, black holes were treated as curiosities. Even Einstein doubted their physical existence. But gradually, evidence mounted. X-ray emissions from binary star systems suggested invisible companions pulling matter into themselves. Stars orbiting invisible centers hinted at unseen mass. And as telescopes advanced, the case became undeniable. At the center of our galaxy, stars like S2 were seen whipping around an invisible point at thousands of kilometers per second. The only viable explanation: a black hole 4 million times the mass of the Sun. It sits in Sagittarius A, quiet but immense, warping space-time around it. And yet, for all their gravity, black holes do not emit light. They are, by definition, invisible. So how do we see something that cannot be seen? We see its shadow. In 2019, astronomers revealed the first image of a black hole's silhouette. It was not easy. It took 8 radio observatories across the globe, synchronized with atomic precision, to peer into the heart of galaxy M87, 55 million light-years away. There, in the core of a giant elliptical galaxy, lies a supermassive black hole billions of times more massive than the Sun. The image showed a ring of glowing plasma, curved by gravity into a perfect circle. In its center, darkness. Not a hole, but a shadow. A silhouette cast by the event horizon itself, outlined by light that barely escaped. This was not an artist's impression. It was an observation. The Event Horizon Telescope used very long baseline interferometry, linking dishes across continents to form an Earth-sized eye. Each observatory recorded torrents of data aligned to nanoseconds. These fragments were assembled into an image that captured not just matter, but the edge of physics. Why was this so profound? Because it confirmed that the warping predicted by relativity is real, even in its most extreme form. The shadow matched Einstein's predictions. Its shape and size told us the black hole's mass. Its stability confirmed the geometry of space-time. This success was not just about one black hole. It proved that with coordination, we could observe the invisible. The same methods have since been applied to Sagittarius A, revealing its more chaotic nature. Unlike M87's quiet surroundings, our galactic center is turbulent, dynamic, harder to resolve. But the principle held. Black holes are no longer abstractions. We measure their spins by the way they drag space-time. We estimate their growth by tracing the jets they launch. And we map their environments by how they shape the matter around them. Through radio waves, we listen to the silence. Through interferometry, we draw the outline of the void. And in doing so, we move closer to understanding not just what lies beyond the stars, but what lies beneath the surface of reality itself. In the shadow of the black hole, science meets mystery, and yet clarity emerges. Hidden behind clouds of interstellar dust and tangled fields of stars lies the center of our galaxy. A region long obscured, but now slowly revealed. For most of history, the heart of the Milky Way was invisible to human eyes. Optical telescopes could not penetrate the dense lanes of dust that stretch across the galactic plane. What lay within remained speculation until we turned to other forms of light. Infrared astronomy opened that hidden core. Unlike visible light, infrared wavelengths can slip through the dusty veils. In the late 20th century, powerful infrared detectors allowed astronomers to peer into the galactic center. What they saw changed our understanding of the cosmos. Near the constellation Sagittarius, roughly 26,000 light-years from Earth, lies a compact radio source known as Sagittarius I. It sits at the very center of the Milky Way, a calm beacon in a storm of stars. For years, its true nature was uncertain, but a series of patient, long-term observations would change that. In the early 1990s, 2 teams of astronomers began tracking the motions of stars near Sagittarius A using infrared telescopes in Chile and Hawaii. Among these stars was one that stood out, S2. It was bright, massive, and on a sharply elliptical orbit that took it incredibly close to the dark center. Over decades, astronomers traced the full orbit of S2, watching it swing in and out like a cosmic pendulum. Every 16 years, it makes a close approach, passing within just 17 light hours of the center. That's roughly 3 times the distance between the Sun and Pluto. At its closest, S2 reaches speeds over 7,000 kilometers per second. Nothing with mass can orbit that quickly unless the object it encircles is immensely dense. The conclusion became inescapable. At the heart of our galaxy is a supermassive black hole, 4 million times the mass of the Sun. There is no other plausible explanation for the gravitational grip that holds S2 and its siblings. Even more remarkable, the orbit of S2 allows us to test the fabric of space itself. According to Einstein's theory of general relativity, massive objects curve spacetime, and moving bodies follow those curves. In extreme gravity, these effects become measurable. As S2 swung around the black hole in 2018, astronomers observed a tiny shift in its motion. A redshift caused not just by its speed, but by the distortion of time itself. This gravitational redshift matched Einstein's predictions with astonishing accuracy. It was one of the strongest confirmations of relativity outside our solar system. And S2 wasn't done yet. Subtle wobbles in its orbit, now being tracked over multiple passes, may reveal even more. The spin of the black hole, the warping of space-time, and the unseen pull of nearby mass. But studying the galactic center is not easy. Infrared telescopes require high-altitude observatories, adaptive optics, and long exposure times. The European Southern Observatory's Very Large Telescope in Chile has been at the forefront of this effort. Its instruments, like gravity and NACO, combine precision optics with interferometry to map the crowded stellar field around Sagittarius A. These tools allow us to resolve individual stars in a region just light days across. It's like spotting a grain of sand in a storm. And what we see is a dance. Dozens of stars orbiting a dark point, each tracing invisible lines through curved space-time. Their paths are not random. They follow the laws of gravity, but in a regime where gravity itself bends the rules. Sagittarius A does not shine, but it does flare. Occasionally, bursts of X-rays or infrared light erupt from its vicinity. These flares are thought to be caused by clumps of matter spiraling into the black hole, heating up before vanishing beyond the event horizon. Each burst gives us a glimpse into the feeding habits of the monster at our galactic heart. Other instruments add to the picture. Radio observatories like the Atacama Large Millimeter Array and the Event Horizon Telescope contribute high-resolution data. By combining infrared and radio observations, scientists can build a multi-wavelength model of the region, tracing not just stars, but gas, dust, and magnetic fields. From these studies, we learn that the center of the Milky Way is a place of extremes, high densities, strong fields, turbulent flows. It is not quiet, but dynamic, not empty, but full of processes that shape the structure and fate of our galaxy. And yet, despite its chaos, the presence of Sagittarius A is stabilizing. Its immense gravity anchors the core of the Milky Way, keeping thousands of stars bound together. Without it, the heart of our galaxy might look very different. By studying the center of the Milky Way, we are not just learning about one black hole. We are exploring the role that such giants play in the life of galaxies. We are testing the limits of physics, and we are turning invisible orbits into maps of space-time. In the swirling hidden center of our home galaxy, we find not darkness, but revelation. For centuries, we looked to the stars and wondered, are we alone? The question lingered in myth, philosophy, and imagination. But only in the last few decades has science found a way to respond. The search for planets beyond our solar system, exoplanets, is one of the most exciting frontiers in astronomy. Not long ago, we knew of only 9 planets, all circling our own star. Today, we know of thousands, and the number grows every year. Each new discovery reshapes our understanding of how common planets are and how unique or not Earth might be. Finding exoplanets is not easy. They are dim, small, and often drowned in the glare of their parent stars. But astronomers have developed ingenious methods to detect their presence, often without seeing the planets directly. The most successful technique is the transit method. When a planet passes in front of its star as seen from Earth, it blocks a tiny fraction of the star's light. Sensitive space telescopes like Kepler and TESS measure these dips in brightness, repeating at regular intervals, revealing the planet's size, orbit, and sometimes even atmospheric composition. Another method is radial velocity. As a planet orbits, it tugs on its star, causing the star to wobble slightly. This wobble shifts the star's spectrum through the Doppler effect: red when it moves away, blue when it approaches. By measuring these shifts, astronomers infer the planet's mass and orbital shape. There are other methods too. Direct imaging, where infrared cameras capture faint planetary light. Gravitational microlensing, where a foreground star's gravity magnifies the light from a background star, revealing hidden planets. And astrometry, measuring minute shifts in a star's position over time. Each method has strengths and limits. Transit works best for planets with short edge-on orbits. Radial velocity favors massive planets close to their stars. Imaging captures wide orbit giants, but struggles with Earth-sized worlds. Yet together, these tools build a fuller picture. Among the thousands of known exoplanets, a few have captured special attention. One such system is TRAPPIST-1, a red dwarf star 40 light-years away, hosting at least 7 Earth-sized planets. 3 lie within the habitable zone, the region where temperatures could allow liquid water. These planets likely have rocky surfaces, thin atmospheres, and orbits so tight that a year lasts just days. TRAPPIST-1 is fascinating not just for its planets, but for what it suggests: that small, cool stars may be ideal places to find habitable worlds. They are more common than stars like the Sun, burn for trillions of years, and their planets are easier to detect. Another intriguing world is Gliese 6167cc, orbiting a star 23 light-years away. It is more massive than Earth, resides in its star's habitable zone, and receives similar energy levels. While little is known about its atmosphere, its conditions make it one of the more promising candidates for life. Yet, we must be cautious. A planet's location in the habitable zone does not guarantee habitability. Atmospheres, magnetic fields, rotation, and geological activity all play crucial roles. A world may have water, but lack stability. It may be sterile or shrouded in clouds of sulfur. Finding life means more than finding water. It means finding chemistry that can persist. New telescopes are refining the search. The James Webb Space Telescope is already probing exoplanet atmospheres, seeking signatures like carbon dioxide, methane, or even oxygen. Future missions like the European Extremely Large Telescope and LUVOIR aim to study Earth-like planets around nearby stars, perhaps even capturing their reflected light. The limits are clear. We cannot yet travel to these worlds. We cannot sample their soils or oceans. But with light, we can still learn. By analyzing spectra, timing, shadows, and wobbles, we extract astonishing detail from across the void. Why do we search? Not just to find life, but to understand our place. If Earth is alone, it is precious beyond measure. If life is common, then nature is more generous than we imagined. Either answer is profound. Each exoplanet is a step closer to context. Each discovery reframes the uniqueness of our world. And one day, perhaps, we may find a pale blue dot circling another sun. Not just a planet, but a second Genesis. The universe, for all its stars and galaxies, is strangely incomplete. What we see, even with the most powerful telescopes, accounts for only a small fraction of what must exist. The rest is invisible, untouchable, and yet unmistakably real. This hidden component is called dark matter. Dark matter is one of the great mysteries of modern cosmology. It does not emit or absorb light. It cannot be seen directly. But its presence is inferred from its gravitational effects. The way it bends light, accelerates galaxies, and holds clusters together. It is the scaffolding upon which the visible universe is built. The story of dark matter begins not with high-tech telescopes, but with a puzzle. In the 1930s, Swiss astronomer Fritz Zwicky studied the Coma cluster of galaxies and noticed something odd. The galaxies were moving too fast. Based on the visible mass, they should have flown apart, but they didn't. Some unseen mass, he proposed, must be holding them in place. His idea was largely ignored, but in the 1970s, Vera Rubin and Kent Ford observed something similar, closer to home. They measured the rotation curves of spiral galaxies, how fast stars moved at different distances from the center. According to Newtonian physics, stars farther out should orbit more slowly, like planets in the solar system. But they didn't. The outer stars were moving just as fast as those near the center. This was not a fluke. Galaxy after galaxy showed the same pattern. The implication was stunning. Most of the mass was not in stars or gas, but in some invisible halo surrounding each galaxy. Dark matter had returned. Today, we believe that dark matter makes up about 27% of the universe. Ordinary matter, the kind we are made of, accounts for less than 5%. The rest, astonishingly, is dark energy, a different mystery altogether. This means that nearly 95% of the universe is composed of entities we do not yet fully understand, and dark matter, though silent, is everywhere. But what is dark matter? That question remains unanswered. It is not made of atoms or anything in the standard model of particle physics. It does not shine, scatter, or decay. But it must have mass. It exerts gravity, and it shapes the universe on the largest scales. The very way galaxies spin, cluster, and evolve cannot be explained without it. Several candidates have been proposed. One is WIMPs, weakly interacting massive particles, hypothetical particles that interact through gravity and perhaps the weak nuclear force, but little else. Another is axions, ultralight particles that may emerge from extensions of quantum theory. Some theorists explore sterile neutrinos, which do not interact via the weak force at all. Others even speculate about tiny primordial black holes formed during the early universe. These are not science fiction. Particle detectors buried deep underground, such as those in the Gran Sasso lab in Italy, or orbiting satellites like Fermi, are designed to catch a glimpse of dark matter. Colliders like the Large Hadron Collider search for missing energy in particle collisions that might hint at new physics. So far, results are elusive, but the search continues, with new generations of experiments offering greater sensitivity. Gravitational lensing offers another powerful tool. When light from a distant galaxy passes near a massive object, like a cluster filled with dark matter, it bends and distorts. This cosmic lensing can map the unseen distribution of mass. The patterns match the predictions of dark matter models. They show invisible webs connecting galaxies, revealing structure where no stars shine. These structures form the skeleton of the cosmic web. Simulations of the early universe also require dark matter. Without it, galaxies would not have formed so quickly. The cosmic web, the vast network of filaments and voids seen in deep surveys, only makes sense if dark matter exists, guiding matter into shape. Without it, stars would struggle to condense. The universe would be a much dimmer, emptier place. Dark matter also explains the internal motions of galaxy clusters. These clusters are the largest gravitationally bound structures in the universe. Yet the visible matter, stars, gas, and dust, accounts for only a fraction of the gravitational mass inferred from the dynamics. X-ray observations of hot gas trapped in clusters also require unseen mass to prevent it from escaping. Yet some dissenting voices remain. Modified gravity theories, like MOND, modified Newtonian dynamics, suggest that perhaps our laws of gravity break down at low accelerations. These models can mimic some effects of dark matter without requiring unseen mass. Others propose that dark matter may not be a particle at all, but a modification in how gravity behaves over cosmic distances. These ideas are bold, but they struggle to explain the full range of observations, particularly gravitational lensing and the early universe. So the mystery endures. We know dark matter is there. We feel its tug. We see its shadow in the dance of galaxies, but we do not yet know what it is. It may be the key to a deeper theory of nature, one that unifies gravity with quantum mechanics, or reveals hidden dimensions. It is, in some ways, a cosmic embarrassment to admit that most of the universe is made of something we cannot identify. But it is also a profound opportunity, a sign that our physics, for all its triumphs, is incomplete. The stars are just the tip of the iceberg. Beneath them lies a deeper, invisible architecture, one that shapes the cosmos not with light, but with mass unlit and unseen. And until we understand it, the story of the universe will remain incomplete. For much of the space age, exploration belonged to governments. Rockets were the tools of superpowers, and missions beyond Earth were measured in prestige, not profit. NASA, Roscosmos, ESA. These names dominated the story of spaceflight for decades. But in recent years, something has shifted. A new wave has arrived, not of flags and anthems, but of contracts and corporations. The commercialization of space is not a vision of the future. It is happening now, reshaping how we reach orbit, who gets to go, and why. Fire, steel, and silicon, the tools of industry, are now the engines of a renewed space race, one driven as much by venture capital as by science. At the heart of this shift is the rise of private launch companies. The most prominent is SpaceX. Founded by Elon Musk in 2002, it transformed from a startup struggling with early failures into the dominant launch provider for NASA, the US military, and satellite operators around the world. Its Falcon 9 rocket, with a reusable first stage, revolutionized the economics of access to orbit. The success of Falcon Heavy and the development of the fully reusable Starship system represent even bolder steps toward frequent, low-cost spaceflight. But SpaceX is not alone. Boeing's Starliner capsule, though delayed by technical challenges, represents a legacy aerospace giant entering the commercial crew market. Developed under NASA's Commercial Crew Program, it is designed to ferry astronauts to the International Space Station, ISS, much like SpaceX's Crew Dragon, which has now completed multiple operational missions with both NASA and private astronauts. The recent milestone of a successful crewed Starliner mission marked an important diversification of US crew transport capabilities. Time, 5 vibes. Sierra Nevada Corporation adds another entry with the Dream Chaser, a winged spaceplane reminiscent of the Space Shuttle. Compact and versatile, it is built for cargo missions and capable of landing on conventional runways. Dream Chaser embodies a different philosophy: less vertical rocket, more orbital aircraft, and expands the variety of how we approach orbital access. Its ability to return sensitive experiments to Earth gently makes it especially valuable for research institutions and NASA science missions. Together, these vehicles mark a fundamental shift in how space is managed. Where once NASA designed, built, and launched everything internally, it now functions as a customer and coordinator. This transition allows NASA to focus on deep space science and exploration, while routine transport is handled by the commercial sector. The agency sets the goals, companies compete to deliver solutions. The reasons are practical. Outsourcing low Earth orbit transportation reduces costs, encourages innovation, and creates a resilient ecosystem. If one provider stumbles, another can step in. This redundancy is no longer a luxury. It is a strategic necessity. Government budgets fluctuate, but a commercial network can adapt quickly to changing conditions. The results have been remarkable. Launch costs have dropped, cadence has increased, the number of satellites in orbit has exploded. A new economy has emerged: telecommunications, Earth observation, remote sensing, navigation, and now space tourism. What was once the domain of astronauts is now open to civilians, scientists, artists, and entrepreneurs. SpaceX has flown private missions like Inspiration, which sent an all-civilian crew into orbit. Axiom Space is building modules for a commercial space station and coordinating missions for paying customers. Blue Origin and Virgin Galactic offer suborbital flights for those seeking the edge of space. The threshold is no longer science fiction. It is a matter of ticket price and waitlist. Of course, commercialization brings its own challenges. Crowded orbital paths raise concerns about debris. Thousands of satellites from Starlink, OneWeb, and other constellations compete for space in low Earth orbit. The risk of collisions increases, threatening both new and existing spacecraft. Space traffic management, once an academic concept, is now a pressing global need. The privatization of critical infrastructure also raises questions of oversight and ethics. Who controls access to orbit? What laws apply in a space economy dominated by private contracts? International agreements like the Outer Space Treaty were not written with mega constellations or lunar mining in mind. The legal framework must evolve as fast as the technology. And yet, the momentum continues. NASA's Artemis program, aimed at returning humans to the moon, relies heavily on commercial partnerships. SpaceX's Starship has been selected to deliver astronauts to the lunar surface. Blue Origin's Blue Moon lander is being developed for later missions. Other private firms are contributing components, software, and support services. The moon is no longer a government-only objective. Commercial lunar initiatives are also on the rise. Companies like Astrobotic and Intuitive Machines are developing robotic landers to deliver cargo and instruments to the moon. Funded in part by NASA's CLPS program, Commercial Lunar Payload Services, these missions pave the way for science and, eventually, industry. Water ice in shadowed craters may support future habitats. Regolith could be used in construction. The first economic footholds on another world are forming. Beyond the moon, Mars is the long-term horizon. SpaceX envisions Starship as the transport system for interplanetary colonization. While that goal remains distant, every test flight and engineering iteration brings the concept closer to reality. Commercial support for planetary science, asteroid prospecting, and deep space communication is already taking shape. This is not a replacement of public spaceflight, but a rebalancing. Public agencies provide direction, standards, and funding. Private companies bring speed, risk tolerance, and market efficiency. The result is a hybrid model, one that merges the pioneering spirit of the Apollo era with the scalability of modern industry. Universities are launching CubeSats. Startups are building propulsion systems. Nations without launch capabilities are buying ride shares. The barriers to entry are falling. The space economy is becoming layered, diverse, and increasingly global. In this landscape, the role of NASA evolves. It becomes less a builder and more an enabler. It funds missions that no market would undertake alone. Flagship telescopes, planetary probes, and deep space observatories. It sets the scientific agenda and ensures access to the frontier remains open. But the spacecraft that deliver the payloads may come from garages as often as from government labs. Fire launches the rocket. Steel holds the structure. Silicon guides the data. In this new chapter, the engines of progress burn not only for science, but for commerce. And with every new capsule, contract, and countdown, space becomes just a bit more accessible. Not only to astronauts, but to us all. The space age is not ending. It is expanding into business, into daily life, and into the realm of imagination once again. For generations, the moon stood as a silent witness to human ambition. In 1969, Apollo 11 made it a symbol of achievement. But after Apollo 17 in 1972, no human has returned. For over 50 years, the moon waited. Now, the wait is ending. NASA's Artemis program represents a bold return to the lunar surface. More than a repetition of Apollo, it aims to create a sustainable presence, using the moon as a stepping stone for deeper space exploration. Named for the twin sister of Apollo in Greek mythology, Artemis signals a new era, one where humanity returns to the moon not as a final destination, but as a beginning. At the core of Artemis is the Space Launch System, SLS, the most powerful rocket ever built by NASA. Taller than the Statue of Liberty and capable of producing over 8.8 million pounds of thrust. The SLS is designed to launch crew and cargo beyond low Earth orbit. Its role is to lift the Orion spacecraft, a deep space capsule designed to carry astronauts safely through radiation belts and on multi-week missions. Orion is not alone in this mission. The Artemis architecture includes a series of evolving missions. Artemis I, an uncrewed test flight, successfully orbited the moon and returned in 2022. Artemis II, set to fly with astronauts, will test human systems in lunar orbit. Artemis III, the centerpiece, aims to land humans on the moon's surface once again, specifically near the lunar South Pole. This choice of location is no accident. The South Pole of the moon is a region of unique scientific and strategic interest. Its permanently shadowed craters may contain water ice, a critical resource for future habitats and fuel production. Sunlit ridges nearby offer long-term solar power. The environment is harsh, but full of potential. A successful landing here would open the door to long-term human presence on the moon. But NASA is not doing this alone. Artemis relies on a network of international and commercial partners. The Gateway, a small space station in lunar orbit, will be built with help from ESA, JAXA, and the Canadian Space Agency. It will serve as a transfer point and science platform, reducing the need to launch everything directly from Earth. For the lunar landing itself, NASA selected SpaceX's Starship as the human landing system, This massive, reusable spacecraft will transport astronauts from lunar orbit down to the surface and back. Starship, with its stainless steel body and futuristic profile, represents a striking fusion of private ambition and public purpose. The Artemis program is not just about flags and footprints. It includes scientific instruments, robotic landers, new suits, surface habitats, and infrastructure. It aims to understand how humans live and work in low gravity, how to extract resources, and how to build systems that can survive lunar nights. It is a dress rehearsal for Mars. That long-term vision is clear. The technologies tested around and on the Moon, propulsion systems, life support, habitat design, and resource utilization are stepping stones toward a crewed mission to Mars. The challenges are greater, the distances longer, the delays unforgiving. But the Moon is close enough to learn and far enough to matter. Mars may lie 200 times farther than the Moon, but the journey begins with lunar dust. Astronauts who learn to navigate the South Pole's shadows, who assemble modules under microgravity, who extract ice and shield from radiation. They will lay the groundwork for going farther. The timeline remains flexible. Artemis III is targeted for mid-decade. Artemis IV and beyond will add cargo missions, advanced rovers, and permanent infrastructure. New suits are being tested. Tools for lunar geology are under design. Communication networks are being planned. Every mission adds a layer. This return is not nostalgic. It is strategic. It is a bridge between what was and what could be. The Moon is no longer a distant memory, but a near future. From the roar of SLS engines to the precision of Orion's trajectory, from the silence of the lunar surface to the chatter of mission control, the journey is not just technological. It is human. It is about learning, adapting, and dreaming forward. The Moon never left us, but we left it. Artemis is the answer to that silence, a message that we are ready to go back and beyond. Of all the worlds we know, Earth is the only one that sustains life. From the oceans to the skies, from the frozen poles to the tropical forests, it is a planet alive in every sense. But its ability to support life is not a given. It is the result of a delicate, rare balance, a long chain of stabilizing forces that work together to keep conditions within a narrow range. Remove one piece and the system falters. The first pillar of Earth's stability is its atmosphere, composed primarily of nitrogen and oxygen. It provides the air we breathe, filters harmful radiation, and traps heat through the greenhouse effect. Without it, Earth would swing between searing heat and freezing cold. But the atmosphere is not static. Its composition has changed over billions of years, shaped by volcanic outgassing, biological activity, and geological cycles. The rise of oxygen-producing photosynthetic organisms was a planetary revolution. In a sense, the atmosphere is alive with the life it protects, and in turn, life evolves to shape it further. Complementing the atmosphere is Earth's magnetic field, generated by the motion of molten iron in the outer core. This invisible shield deflects solar wind and cosmic rays. Without it, our atmosphere would be stripped away over time, as likely happened on Mars. The field also stabilizes conditions on the surface, shielding life from radiation and maintaining the integrity of our climate systems. Periodic reversals of the magnetic field are recorded in the rock layers, but its protective function endures. Then there is the Moon. Unusually large for a planet of Earth's size, our Moon plays a quiet but critical role. Its gravitational influence stabilizes the tilt of Earth's axis, which in turn regulates the seasons. Without the Moon, Earth's tilt could wobble chaotically, leading to extreme climatic variations over geologic timescales. The moon also drives the tides, mixing ocean layers, influencing marine life, and possibly aiding in the early chemical pathways that led to life. Its presence is not just poetic, it is foundational. Earth's internal dynamics also contribute. Plate tectonics, driven by heat from the planet's interior, continually reshape the surface. They recycle carbon, build mountains, and create habitats. The shifting of continents alters ocean currents and climate patterns, sometimes gradually, sometimes catastrophically. Volcanic eruptions release gases that influence temperature and air chemistry. Earth breathed through these geological processes. Climate itself is a fragile system. Earth's temperature has remained within life-supporting limits for billions of years, thanks in part to feedback mechanisms like the carbon cycle. Volcanoes release CO2. Plants and oceans absorb it. Weathering of rocks draws carbon from the air. Ice reflects sunlight, while forests absorb it. These systems interact in complex, often self-correcting ways. But when thresholds are crossed, feedbacks can turn reinforcing rather than stabilizing, as seen in past extinction events. One driver of long-term climate patterns is the Milankovitch cycles, slow variations in Earth's orbit and axial tilt. These cycles, named after Serbian astronomer Milutin Milankovitch, alter the distribution of sunlight on Earth's surface. Over tens to hundreds of thousands of years, they influence the advance and retreat of ice ages, shaping the rhythm of glacial and interglacial periods. The shape of Earth's orbit, eccentricity, its axial tilt, obliquity, and the wobble of its axis, precession, all combine to modulate solar input. The story of Earth's climate is written in ice cores, ocean sediments, and fossil records. We know that 56 million years ago, the planet underwent a rapid warming event called the Paleocene-Eocene thermal maximum, linked to massive releases of greenhouse gases. We know that during the snowball Earth periods, ice may have covered much of the globe. Yet life endured, evolving, adapting, persisting. Life did not merely survive. It learned to thrive in shifting climates, from the first single-celled organisms to complex ecosystems. Life, in turn, shapes the planet. Photosynthetic organisms transform the atmosphere by producing oxygen, leading to the Great Oxidation Event around 2.4 billion years ago. The evolution of land plants accelerated rock weathering, drawing down CO2 and cooling the climate. Microbes and animals contribute to nutrient cycles. Coral reefs build limestone skeletons. Earth's biosphere is both a product and a regulator of its long-term stability. But this balance is not guaranteed. Today, human activity introduces rapid changes. Greenhouse gas concentrations are rising at rates not seen in millions of years. Deforestation, ocean acidification, and biodiversity loss strain Earth's resilience. We are, knowingly or not, testing the limits of the very systems that make life possible. The speed of current change challenges feedback systems that evolved over millions of years. And yet, Earth remains a marvel of coherence. Its orbit is nearly circular, avoiding extreme temperature swings. Its size allows it to retain atmosphere, but not crush with gravity. Its position in the solar system places it within the habitable zone. Its magnetic field, plate tectonics, ocean circulation, and the cloud systems all function in concert. The balance is dynamic, not static. It is alive. It is easy to overlook how rare this is. The planets we have found beyond our solar system show the diversity of worlds. Some scorched, some frozen, some tidally locked, some bathed in radiation. Among them, a world with Earth's particular combination of traits is not yet known. Earth is not average. It may be exceptional. The fragility of Earth is not a weakness, but a feature. It is what makes it dynamic, responsive, and alive. The challenge is to understand that balance and to maintain it. For in all the universe we can observe, this pale blue dot remains the only place where the story of life continues to unfold. We live not just on a planet, but within a system of interwoven processes, geological rhythms, biological cycles, and celestial influences. The Earth is not merely a setting for life. It is a partner, a cradle. And like all things living, it must be understood, respected, and protected. For all our journeys into space, Earth is still our only home. Long before satellites circled the Earth, our understanding of weather and climate was limited to what we could observe from the ground. Barometers, thermometers, weather balloons, all useful but partial. We could see clouds above, but not their full sweep. We could measure temperature at the surface, but not patterns across oceans or continents. That changed with the advent of eyes in the sky. In 1960, the launch of TEROS-1, television infrared observation satellite, marked a quiet revolution. A small cylinder equipped with television cameras, TEROS showed for the first time what Earth looked like in motion from orbit. Swirling clouds, vast storm systems, and polar ice came into view, not as scattered data points, but as living systems. Meteorology would never be the same. TEROS was followed by the Nimbus series in the 1960s and 70s, which added infrared and microwave sensors. These satellites could measure not only visible cloud formations, but also temperature profiles, moisture content, and radiation balance. For the first time, scientists could study the full vertical structure of the atmosphere, day and night, pole to pole. Then came the Copernicus program, the European Union's flagship Earth observation effort. Launched in the 2010s, it provides a continuous stream of data from Sentinel satellites, monitoring everything from sea level and forest cover to greenhouse gas concentrations. With Copernicus, Earth observation became global, systematic, and sustained. Together, these satellites have created an unbroken visual record of our planet. They orbit hundreds of kilometers above the surface in polar or geostationary paths, scanning oceans, clouds, ice sheets, vegetation, and the shifting patterns of climate. Their instruments see in infrared, ultraviolet, microwave, and radar. Some detect temperature, others track aerosols, pollution, or sea surface height. Each is a sensor, together forming a planetary nervous system. One of the most vital roles of satellite observation is the tracking of greenhouse gases. The Keeling curve, a graph of atmospheric CO2 levels measured since 1958 at Mauna Loa, provided early warning that something was changing. Satellites extended this insight globally. Missions like NASA's OCO2, orbiting Carbon Observatory, and Japan's GOSAT allow scientists to map carbon dioxide and methane concentrations across the entire globe, season by season. These measurements confirm that human activity, especially the burning of fossil fuels, is driving unprecedented changes. CO2 levels have climbed from 315 parts per million in 1958 to over 420 ppm today, a level not seen for millions of years. The warming associated with this rise is recorded by satellites in sea surface temperature, glacial retreat, drought patterns, and shifting vegetation zones. The ozone layer too became a focus of space-based monitoring. In the 1980s, satellites detected a dramatic thinning of ozone over Antarctica, later termed the ozone hole. It was traced to chlorofluorocarbons, CFCs, chemicals used in refrigeration and aerosols. The response was swift. An international treaty, the Montreal Protocol, phased out CFCs. Subsequent satellite data showed gradual healing. It remains a rare success story in global environmental action enabled by space-based observation. Beyond atmospheric chemistry, satellites monitor ice sheets in Greenland and Antarctica. They measure changes in mass, volume, and velocity. They map the melting of Arctic sea ice, the retreat of glaciers, and the collapse of ice shelves. Missions like GRACE and IceSat use gravity and laser altimetry to track changes in ice thickness and water flow. The loss of ice is not just a regional concern. It drives sea level rise worldwide. Oceans too are under watch. Satellites monitor sea surface height, currents, salinity, and phytoplankton blooms. They detect El Niño and La Niña events, which influence weather patterns globally. They map coral bleaching, track marine heat waves, and help model hurricane intensity. Our ability to forecast and understand the ocean climate system depends on these instruments in space. Vegetation and land use are another frontier. Instruments like MODIS on NASA's Terra and Aqua satellites monitor greenness, land cover change, deforestation, and fire. They reveal the seasonal pulse of plant life, a planetary heartbeat driven by sunlight, moisture, and carbon. They track agricultural productivity and drought, informing food security policies. Even human infrastructure is visible from space. Nighttime lights show the spread of cities. Radar detects roads and buildings. Thermal sensors reveal energy use and heat islands. Satellites assist in disaster response, mapping damage from earthquakes, floods, and wildfires. They are silent observers, but their data moves quickly to inform decisions on the ground. Climate models rely on this observational backbone. The patterns satellites reveal of warming, drying, storm activity, and feedback loops are fed into simulations that help us understand what lies ahead. Are storms growing stronger? Is the Amazon drying? Will melting permafrost release more carbon? These questions are rooted in satellite data. Space-based observation also fosters international collaboration. Agencies like NASA, ESA, JAXA, and ISRO share data. Networks like the Global Climate Observing System integrate measurements across domains. Open data policies ensure that scientists around the world can access, analyze, and apply what the satellites see. The planet becomes a shared subject of study. Yet these tools are fragile. Satellites degrade, orbits decay, funding ebbs and flows. The loss of a key instrument can leave blind spots in our knowledge. Maintaining a robust, overlapping network of satellites requires foresight, investment, and coordination. It is a form of planetary stewardship, not of ecosystems directly, but of the systems we use to understand them. And still, satellites only show what is. They do not tell us what to do. They offer warning, not solutions. It is up to us to interpret, decide, and act. The ozone hole closed not because of satellites alone, but because nations responded to what the satellites revealed. The same is true for climate change, for deforestation, for sea level rise. In the quiet orbits above, the instruments continue their vigil. They see no borders. They carry no flags. Their data flows to all who ask. They are eyes in the sky, and through them, Earth is learning to know itself. Communication has always defined the boundaries of civilization. From smoke signals to fiber optics, each new leap has brought distant voices closer, shrinking the world into networks of shared knowledge. In the 20th century, the sky itself became part of that network. The launch of Sputnik in 1957 marked the beginning of the space age, but it also marked the dawn of orbital communication. Sputnik's beeping signal broadcast on shortwave radio, was simple. Yet it was the first artificial message from orbit heard around the globe. It signaled a new possibility to use space not only for observation or exploration, but for conversation. Within a few years, satellites were being built with antennas, transponders, and repeaters, tools for relaying messages across continents. In 1962, Telstar made history. Launched by NASA and AT&T, it relayed the first live television images between Europe and the United States. Viewers saw the Statue of Liberty and the Eiffel Tower in real time. Voice, video, and data now had a new path. Up through the ionosphere, across the vacuum of space, and back to Earth. Since then, communication satellites have multiplied. Most operate in geostationary orbit, about 36,000 kilometers above the equator. There, a satellite orbits at the same rate the Earth rotates, appearing fixed in the sky. This allows ground dishes to remain pointed in one direction, maintaining constant links for television, radio, internet, and phone service. But geostationary orbit is not the only solution. Low Earth orbit, LEO constellations like Iridium, Globalstar, and more recently Starlink and OneWeb use swarms of satellites flying at altitudes of 500 to 2,000 kilometers. These move quickly across the sky, handing off signals in a seamless relay. Though they require more satellites to provide coverage, their proximity to Earth allows for lower latency and higher bandwidth, crucial for real-time communication. Beyond public telecommunication, space agencies developed their own dedicated relay networks. NASA's Tracking and Data Relay Satellite System, TDRSS, operational since the 1980s, maintains near continuous contact with the International Space Station, the Hubble Space Telescope, and various Earth-observing satellites. Without TDRSS, missions would be limited to brief contact windows as ground stations passed overhead. In Europe, the EDRS, European Data Relay System, builds on this idea. Nicknamed the Space Data Highway, EDRS uses laser communication terminals to transfer data between low-orbit satellites and geostationary relay satellites, which then beam the information down to Earth. The speed is extraordinary. Terabytes of Earth observation data can be delivered in near real time, supporting everything from natural disaster response to agricultural planning. Laser-based communication represents a leap forward. Unlike traditional radio waves, lasers can carry more data at higher speeds, with tighter beams that are harder to intercept or jam. They require precise pointing and tracking, but offer the promise of optical links between satellites, spacecraft, and eventually planetary outposts. NASA's LCRD, Laser Communications Relay Demonstration, and the Artemis program's optical terminals are early steps in this evolution. As data flows grow, the importance of secure, resilient space communication increases. Satellites enable global navigation systems like GPS, GLONASS, Galileo, and Beidou. They provide timing for financial transactions, positioning for transportation, and coordination for emergency response. Disruption of these services, whether by accident or intention, can ripple across societies. Space communication also supports deep space missions. Probes like Voyager, New Horizons, and the Mars rovers send their signals across vast distances to NASA's Deep Space Network, a trio of enormous antennas located in California, Spain, and Australia. These dishes, up to 70 meters in diameter, track faint whispers from the edge of the solar system. A message from Mars can take minutes to arrive. One from interstellar space can take over a day. Maintaining contact with such distant travelers requires not just power and precision, but patience. Engineers must schedule time for each probe, calibrate signal strength, and process delayed transmissions. A command sent today may not be confirmed until tomorrow, but the system works. Even now, decades after launch, the Voyagers continue to send back data from the edge of the heliosphere. In Earth orbit, the trend is toward integration. Military, civilian, and commercial systems increasingly share hardware, frequencies, and data paths. Satellite internet services are expanding to remote regions. Aircraft, ships, and autonomous vehicles use satellite links for constant navigation and reporting. In emergencies, satellite phones maintain contact when ground networks fail. The vision is moving toward a seamless, space-based internet, a mesh of ground stations, satellites, airborne nodes, and planetary relays. Technologies like inter-satellite links, adaptive routing, and AI-managed bandwidth allocation are under development. Space is no longer just a vantage point. It is becoming the backbone of our digital lives. And it goes beyond Earth. Future missions to the Moon and Mars will require robust communication systems. Lunar orbiters will act as relay stations for landers and rovers. Starship and Orion will need high-bandwidth links for telemetry, voice, and video. On Mars, a similar infrastructure must evolve. Orbiters, land-based antennas, and perhaps even laser links to Earth. The interplanetary internet is not science fiction, it is a roadmap. Yet for all its complexity, space communication still relies on fundamentals: electromagnetic waves, vacuum propagation, and the geometry of orbits. What changes is scale, precision, and ambition. The signals we send across the void connect not just machines, but minds. Messages from space tell us about solar storms, atmospheric shifts, missing planes, and distant planets. They carry the news, guide our paths, and relay our voices. From a whisper over Sputnik's shortwave to gigabits streaming through lasers, the journey has just begun. Space, once silent, now hums with traffic. And in that steady hum, Earth listens, speaks, and remembers its place in the cosmos.